Good morning and welcome to today's Machine Design and Power in Motion webinar. Our topic today is Winning Against Corrosion in Fluid Power Systems, sponsored by Parker Hannifin. I'm Bob Vavra with Endeavor's Design and Engineering Group. Let's talk about how you can participate in today's presentation. If you have any technical difficulties during our session, type your question in the Ask a Question box and a member of our team will assist you. You can also click on the question mark Help button in the upper right corner of your screen. We also welcome your questions during our event today, and we'll get to as many of those as we can during the Q&A session that follows the main presentation, so feel free to send in your questions at any time. To do so, simply type your questions into the Ask a Question box and click on the Send button. If you'd like a copy of this presentation, please click on the Event Resources tab on the side of your screen to download the presentation. Also, today's session is being recorded and will be available on the Machine Design and Power in Motion websites within the next week. You'll be notified by email when the archive is available. So let's meet our presenters for today. Brian Smith is the Business Development Manager for Parker's Tube Fitting Division. In his 28 years in the fluid power industry, he's gained extensive experience through specifying technical solutions and troubleshooting customer fluid conveyance systems. He frequently serves in lead roles on the development and qualifications of new products and services, including corrosion-resistant technology. And Yindong Ji is a material scientist with 15 years experience in surface engineering, corrosion science, electromechanical processes, and material development. He's currently leading the Metals Innovation Center of Parker in Columbus, Ohio, where he leads the development of innovative surface protection technologies for fluid power components. This is an important topic for our audience, gentlemen, and we're really looking forward to today's presentation.
Well, thank you very much, Bob. It's a pleasure to be here today to discuss corrosion for the fluid power industry, specifically fluid connectors, hydraulic adapters and fittings, as we say. Here's an agenda or a rough idea of what we'll be covering today. And of course, we will certainly leave some time at the end for some questions. I look forward to, Yindong and I both look forward to addressing those towards the end. So first of all, fluid connectors. There is a corrosion dilemma on these fluid power connectors. Corrosion is actually considered an enemy of metallic components throughout industry, especially in fluid power. It'll take hold quickly, sneak up on you, causing downtime and ultimately devaluation of the equipment that's been invested in. But the industry is becoming a bit less tolerant of corrosion, but with proper material selection, the use of advanced corrosion-resistant technologies, in fact, we'll be talking about some of those today, the fight against corrosion is certainly becoming less of a losing battle. So from an equipment OEM standpoint, the impact of corrosion goes well beyond simply making it through that first planting season for the ag world, or the first 100,000 road kilometers for a transportation customer, or 2,000 operating hours, or whatever that threshold or benchmark might be. Useful life of the equipment's increasing, meaning also that fluid power connectors and conductors also are expected to last longer from corrosion. Long-haul export is another corrosion. We live in a global environment or a global world, products being shipped all over the world. Ensuring that equipment arrives in pristine or factory condition, regardless of the country of manufacture and end destination, is paramount. And from an end user standpoint, productive hours and uptime is everything. Corrosion is not just unsightly as well if you think about it. Maintaining highly corroded or severely corroded components requires a lot more time and eventually replacement. And unlike your house or your residence, you can't simply just add another paint layer because it doesn't solve the problem. So let's dig in a little bit deeper here. So what exactly is the cost or the impact of corrosion? So there are many studies on this, but this happens to be one here that is recognized throughout our industry. It's published by NACE, now part of ANPP, that states that $2.5 trillion annually is what's estimated to be the cost of corrosion on a global basis. For perspective, that's about 3% of global GDP. In fact, even further perspective, that's larger than the GDP of some of the largest industrialized economies, such as Italy, Brazil, or even Canada. While the study acknowledges that it's going to be different by region based upon geography, based upon the GDP and exactly what they produce, so again, different by region, you can see how the overall costs are distributed with this pie chart here, whether that's agricultural and forestry, services, mining, industrial, or general industry category is shown here that is broken down with mining and manufacturing, construction. Certainly fluid power is spread relatively diversely in all of these segments. And as a result, certainly we have a contributing factor in this $2.5 trillion cost. Fluid power connectors or conductors and this equipment is going to exhibit a degree of corrosion over time. However, the operating environment is critical and certainly one of the most foretelling or predicting factors of when, how, and if a product will corrode. For in-plant equipment, what we often call industrial, the equipment's typically in a controlled environment. So equipment in this environment is going to be, just by default, less susceptible to corrosion, especially early on, and especially as shown here on the left, if there is a paint that's been applied to these fluid connector type products. However, if there's an agent for corrosion, such as exposure to chemicals or frequent washdowns or excessive humidity, certainly there's going to be a higher propensity for corrosion. On the other hand, as shown on the right, a non-controlled environment, such as those typical in mobile transportation, agricultural segments, they are going to see signs of premature corrosion on the fluid connectors simply due to the exposure to the elements, as well as the dynamic or what we say inconsistent duty cycles for this type of equipment. So the equipment and the owners of these equipment in these segments, they certainly are going to have a lot more concern about corrosion. Now, you heard me mention the term corrosion agent or corrosion catalyst. Now, these are directly related to the operating environment of the equipment. You can see several factors listed here. Some are obvious, but maybe some are not. So, for example, exposure to salts, which is common in trucks, mining, and of course, marine or maritime vessels, shipbuilding, etc. That is an obvious corrosion agent. Exposure to fertilizers, as seen with equipment used in agriculture, whether that's direct exposure or incidental exposure. And of course, excessive humidity, and that's often a function of geography. But as mentioned before, in today's global economy, equipment that's shipped all around the world, we're using this new term called sea freight corrosion, which is becoming more and more of a challenge these days for products when they're shipped overseas. Clearly, these agents for corrosion also have a cumulative effect. For example, think about exposure to fertilizers in a very humid growing climate. So they have a cumulative effect and really can be additive or pile on, if you will. So the takeaway here is really that the equipment OEMs or fleet owners, they don't always know the specifics of where that equipment is going to be subjected due to different duty cycles, different applications. So sometimes this corrosion can clearly sneak up on you or even catch you off guard. From an MRO standpoint, maintenance, repair, and operations, equipment owners, primarily here, once corrosion actually starts, it's difficult to turn back the hands of time. You could actually say impossible to turn back the hands of time. The upkeep of products, certainly with moderate to severe corrosion, is actually quite costly. More frequent and more difficult maintenance occurs. So when the corrosion of connectors takes hold, like for example on this one here, on the image on the left where that severe corrosion is taking place, maintenance on that equipment is extremely difficult. Wrenching flats are compromised. Typically in our industry, you require 2 wrenches. Something's going to break off simply due to corrosion there. Corrosion migration or spread. It also can migrate, corrosion can migrate from component to component. And adapters are often thought of afterthoughts, but they really do serve as a key bridge between very expensive hydraulic components such as pumps, valves, motors, accumulators, cylinders, over to maybe flex connections or tubes. So making sure that these components aren't an agent for spread is critical or paramount, something that's often overlooked. And then of course productivity, unproductive or underutilized equipment is all bad if you can say that. From having products sitting at the dealer or in your shop being repaired due to corrosion, is certainly a cost that has to be considered. And then ultimately the replacement cost of the actual component that will undoubtedly need to be conveyed or replaced over time. From an OEM standpoint, equally concerning. So when your company's name is on the equipment, it means something. And if there's corrosion, that does not reflect well on your output. However, it does go well beyond aesthetics here. So we hear from prospective customers all the time, fittings shouldn't corrode while they're on my dealer's lot or in transport, or like I said before, long haul overseas freight. There's a cost associated with that. If you look at this backhoe, this line of new backhoes here, there's some corrosion already starting on these connectors, and these particular these particular pieces of equipment haven't even been commissioned or used yet. So this ultimately could turn into a warranty claim to the end customer or the dealer, resulting in labor expended and, of course, replacement materials, and not to mention the reputation and aesthetics. So what do we do about it? Well, certainly material selection is an option. So engineers have a range of options that can be employed to reduce or help prevent corrosion, and material selection is a big part of that. But before we go into a semi-deep dive on the different material options that are commonly used in the fluid power segment, I'd like to do a little shout out to what we use in our industry as a selection tool called STAMP. Now, STAMP is an acronym in the fluid conveyance world for technical product selection, and it's typically started with STAMP. It's easy to remember, and those 5 letters mean size, temperature, application, media, and pressure. So the appropriate selection of a fitting or an adapter for corrosion resistance factors, it seems pretty obvious. It's related obviously to the media, right? What's being conveyed through that product. However, compatibility on the outside is also critical as well, such as environmental compliance or environmental acceptance or compatibility, but then also temperature can affect corrosion as well. From the previous slide, you probably saw that temperature was listed as a corrosion agent, and it certainly is. On the other hand, a product that may be very well suited for corrosion resistance may have some other offsetting benefits or offsets to those benefits in the form of reduced pressure holding capability or maybe commercial implications such as availability or cost. So getting into those 3 different common material options, again, not a deep dive here, but just kind of a basic overview that should be helpful. The first one is brass. So brass is an alloy of copper and zinc, and because it contains no iron, it will not rust, but it will oxidize or tarnish over time, and that can be seen with a green tinge, but again, it will not rust. But for fluid power, especially heavy duty cycle or high pressure fluid power application, brass is generally considered to be a moderate strength and toughness. It simply does not hold up to heavy duty cycles required in the fluid power industry, but very good for coolants, lubricants, gas, transportation, fuel, and other type of low to medium pressure applications. Stainless steel. So stainless steel is an alloy of steel that contains more than 10.5% chromium by definition. So typical alloys used in the fluid power segment are going to be 316 or 316L, but tubes and connectors can also be made of 303 or 304. Both, I think all 3 being austenitic stainless steel grades. It really does provide the ultimate in corrosion resistance. Great for chemical compatibility, media compatibility, overall corrosion resistant. It's often the default choice for aggressive applications where the media or surrounding environments is corrosive. Good resistance to acids as well if your equipment might be exposed to that. Very high pressure rating, equivalent or comparable or even sometimes higher depending on the grade than carbon steel. Good temperature range as well. However, the offset to that, of course, stainless steel is not as commercially viable because of availability, and it's significantly more expensive. Carbon steel. So carbon steel, by definition, is an alloy of iron and carbon. It's also alloyed with other metals to improve strength, toughness, machinability, and other factors. And really, by far, it's the most common material used for fluid power conveyance, and whether that's industrial construction, ag equipment, or any of the segments that fluid power participates in. And the reason why it's high strength, good temperature resistance, common availability, in general, low cost. However, from a corrosion standpoint, which is really why we're here today, it does not provide great corrosion resistance and not even comparable to stainless or brass. In fact, because it has iron, it absolutely has to be protected to prevent it from corrosion, typically with electroplating in our industry, and my colleague Yindong will speak to that in just a few moments. So really, corrosion resistance in the fluid power industry on connectors in particular really has to be a balance of all these factors. So often they're competing though. So whether that's media compatibility, temperature rating, strength, the pressure holding capability, even the durability, and also the commercial applications have to be balanced against corrosion resistance. So that's again why we in our industry use that iterative stamp process to help dial in these best attributes when undertaking, product material selection.
Now let's take a deep dive into the technical aspects of corrosion. We're going to talk about what are corrosion, how corrosion forms, and what are the most common technologies that we use in fluid power systems to manage corrosion. So first of all, when we look at this picture, every one of us would immediately recognize that is rust. And yes, and rust is the most common forms of corrosion, one of the most common forms in our life. And corrosion, by definition, is an electrochemical reaction. When corrosion occurs, it oxidizes a metal ion atom and make it a corrosion product. And corrosion can damage part or the entire object when it occurs. There are, in general, 6 most common forms of corrosion, defined by the mechanism, how to form, where to form, what makes it happen. But in fluid power industry, the most common form and most important form of corrosion is uniform corrosion. Uniform corrosion is a type of corrosion. When it happens, the attacks proceed evenly over the entire surface or a large fraction of the surface. Compared to the uniform corrosion, all rest forms of corrosion are heavily localized. And for our today's talk, the uniform corrosion is our topic. The uniform corrosion, when it happens, the material got thinner evenly over the time until failure occurs. So I like to use this illustration on the top to better explain the basics of corrosion, especially uniform corrosion. So as mentioned, it is a type of the electrochemical reaction. Therefore, it requires 4 essential elements at every electrochemical reaction. Anode, that's where the oxidation reaction takes place. Cathode, that's where the reduction reaction happens. And electrolyte, that is a passage for ion to transport within the corrosion cell. And last but not least is an electrical connection. You see the connected anode to cathode and help electron to transport in that direction. For uniform corrosion, the anode and cathode evenly distribute over the surface. That makes the result as those examples that were shown on the picture. Corrosion evenly proceeds. So in our industry, there are several typical methods that we use to manage corrosion. One of them is painting. Everyone knows what paint is. It provides a barrier layer, isolates the steel substrate from the corrosive environment. And paint is often applied after hydraulic tube fittings are assembled. But painting is very thick, and it's also brittle. It does not withstand deformation well. So we cannot rely on painting to protect unassembled products. Then galvanizing and electroplating, both technologies, on the other hand, provide a sacrificial layer. Galvanizing is done by dipping the articles into molten zinc. The galvanizing can be commonly seen on industrial piping and plumbing fittings, but galvanizing layer is also pretty thick and makes it not suitable for precision hydraulic tube fittings and adapters. So electroplating is most common used in fluid power systems. I like to use the illustration on the left to show the basics of electroplating. If you remember the illustrations for that corrosion cell, you may see the electroplating shares a lot of similarities with corrosion. That's because electroplating is also another form of electrochemical reaction. So it shares all essential elements. But different from corrosion, which can happen by itself, electroplating cannot spontaneously take place. An external power source is required to turn the already oxidized metal ion back to its metallic form and deposit it on the substrate. The picture on the right-hand side is one example of the red plating process that we use commonly in our industry. And hydraulic tube fittings, adapters, and their components can also be plated by a barrel process. Let's look into several types of most common electroplating. So we would show cadmium plating, and some of you may still remember that cadmium plating was commonly used because it has excellent corrosion protection as well as ductility and many other properties. However, cadmium is highly toxic poison. Therefore, the use of it has been heavily regulated over the years. Zinc electroplating was introduced over the last 20-30 years as a compromised offering to replace cadmium. Zinc plating has its own benefit. However, it only offers moderate corrosion protection in many applications. As a result, the ongoing effort to continuously improve the corrosion protection of electroplating never stops. And zinc-nickel electroplating has been introduced as one of the most recent advances. Zinc-nickel plating is the alloy of zinc and nickel. It has better electrochemical properties compared to zinc when we apply it on a steel substrate. Therefore, it can offer significantly higher corrosion protection than zinc plating. That means it can last longer in many applications, but also it opens new opportunities for applications in more demanding environments that zinc doesn't do well. There are drawbacks associated with zinc-nickel plating as well. It is using a more expensive chemistry due to the addition of more expensive nickel metal. And it has different physical properties from zinc plating. So historically speaking, there is some difficulty to control the friction on threaded fittings. That will translate into issues over assembly performance. By far, we covered what is corrosion and how electroplating are used to manage corrosion in fluid power systems. We're going to talk about in industry how the corrosion protection of those electroplating systems are evaluated. Over the years, accelerated testing protocols are developed to determine the performance of coatings and platings. There are in general several categories: humidity test, soft spray test, and cyclic corrosion test. They accelerate corrosion in a laboratory controlled environment. And several industrial governing bodies such as ISO, ASTM, SAE International, they all determine and publish standards to specify how each different type of corrosion test need to be done. The humidity test is mainly used for coating and painting. So in our talk, we'll introduce soft spray and cyclic. Neutral soft spray test. That is one of the most common corrosion tests accepted in industry. There are a few equivalent standards specify how that need to be run. When to set up a neutral soft spray test, several critical parameters such as pH, temperature, salt solution, and pressure are set as constant. pH is neutral as indicated by the name, and the 5% salt solution is constantly being atomized and making fog to supply into the chamber. There's drawback of the neutral soft spray test because, as you can see, everything is set as constant. Therefore, there's a static stay in the chamber. But in our real life, really corrosion events occurs at steady state. Therefore, the neutral soft spray test, as commonly accepted as it is, does not provide a very good correlation with the real-world exposure. Therefore, over the years, a series of cyclic corrosion tests are developed and evolved. Cyclic corrosion test combines segments such as soft spray, rain shower, and fluctuated temperature and humidity cycles. For example, dry heat over lower temperature but higher humidity to create condensation. And those critical segments are operate in a circle throughout the test. Cyclic corrosion test duplicates natural occurring corrosion events under a well-controlled environment. Therefore, cyclic corrosion tests can provide better correlation with the real-world exposure. Here, the illustration on the left gives you an idea, a typical look of the environmental chamber where those corrosion tests are conducted. And when we run corrosion tests, there are a few things to pay attention to. The typical corrosion products are listed here, and we are going to get into details of each one of them in the following slide. Pass or fail criteria. Though different end users may develop their own requirements, all those criteria is based on how long the part is in the test and the extent of corrosion of the plating after the test. For example, SAE International, the governing body of hydraulic tube fittings and adapters, published the minimum protection requirement in accordance with the neutral soft spray test is no appearance of a plating corrosion before 96 hours and no appearance of substrate metal corrosion before 144 hours. Now let's look at the several types of corrosion products with more detail. First of all is the white rust. White rust is a white and voluminous corrosion product commonly found on zinc. The word voluminous means it has volume. And white rust typically is a mixture of zinc oxide and zinc hydroxide. When you touch it, it gives you a chalky or a waxy touch and has porous structure. That porous structure opens a passage for corrosion agent to further attack the metal substrate underneath the plating. And it's also highly visible. The white rust can form anywhere between days and months after test starts. Of course, that depends on how severe the corrosion test you choose and the quality of the plating. But once the white rust appears, that means that sacrificial protection layer is being consumed. And typically, red rust will quickly follow. Now let's look at red rust. No need to explain, everyone knows that's how iron and steel got oxidized. When we see the appearance of red rust, that means the sacrificial layers already consumed, at least in that local area. And corrosion attacks proceed on the metal substrate. Over the test, there are a few things to look for. First is the time to the initial appearance of the red rust. On top of that, different customers may develop their own standard, such as some manufacturers use a certain percentage area of the product covered by red rust before a certain amount of time as their pass or fail criteria. And when red rust appears on hydraulic tube fittings, there are a few areas they oftentimes unseen. That is, the post-plating parts that need deformed after plating. And my colleague Brian will provide detailed discussion on that. The corners as shown on this picture and other areas that are difficult to plate. Lastly, there's another corrosion product that's easily confused with white rust. It is called white haze. White haze is typically found on the surface of zinc-nickel plating. It is a thin and non-voluminous corrosion product. It has dense structure as opposed to the porous structure of zinc plating, corrosion product of zinc plating. And when a dense white haze forms, it becomes a barrier layer that slows down the further progression of corrosion. White haze is not textured and it's not even visible when it's wet. White haze can quickly happen over the corrosion test on zinc nickel, but as explained, it's very slow to progress.
So, cyclical corrosion testing, salt spray testing, white rust, red rust, white haze, a lot of different things out there. So from a fluid connector standpoint, how does this all relate? So as a review, most of the connectors out there are steel, as we've already discussed. Steel requires corrosion protection, typically through electroplating. In our industry, the current state is most adapter manufacturers are using zinc plating. However, there are zinc-nickel derivatives that are becoming more common, especially on a custom basis. Here's the thing, though. Corrosion performance varies dramatically in the industry. So, and that's from manufacturer to manufacturer, and even within the same manufacturer from product to product or product series. So there's a high degree of variation, if you will, on corrosion performance in salt spray in particular. Additionally, our industry actually allows some exceptions for some of the difficult areas of plating. So as Yindong had mentioned, crest of threads, sharp points, serrations, areas that are difficult to maintain plating, there's actually exceptions and allowances in our own governing body that say, well, you don't have to meet the full published corrosion resistance. We'll take exceptions there. Products also that are deformed after they're plated, such as backup washers, or in this case here, you can see a fitting that has a crimp nut on it that's been heavily deformed in order to make a male by female swivel connection. So these industry exceptions are just accepted, for a lack of a better term, in our industry. However, when it comes to plating, the industry, including Parker, continues to develop incremental improvements over time for hydraulic fittings and adapters especially. However, the industry continues to expect more than what's being offered, or the customers expect more than what's being offered by the industry. So when we collaborate with customers regarding corrosion resistance, this is kind of the laundry list, if you will, or the common themes that they provide to us on what's expected in relationship to corrosion protection. So first and foremost, longer corrosion resistance. 1,000 hours should be a minimum for salt spray resistance. And also products that are subjected to maybe long haul sea freight, corrosion, or that incidental contact with exposure shouldn't have to worry about what we call that passive use corrosion or pre-commissioning or pre-use corrosion. Minimize the exceptions. I just talked about the exceptions in the previous slide. But if a manufacturer publishes XX hours of salt spray resistance, the entire product should withstand that, not, well, with the exception of a sharp thread or a corner or a crimp nut or a backup washer. So, and this one here is really important. And it's don't mess with my assembly torques is really the underlying theme there, but it really should be drop-in compatible. No changes to assembly torques, whether that's assembly procedures, torques, flats, whatever that might be. I should be able to use zinc-nickel, or other types of products without modifying the assembly torques, and then also beyond salt spraying. Give me something that goes beyond just the static salt spray test, where it's sitting in a chamber for 500 hours or 250 hours, because that's not really how my product is used in the industry. So using this feedback and our engineering and manufacturing capability, we developed Toughshield Plus. It is our new standard plating on all carbon steel tube fittings and adapters, and it'll prevent corrosion significantly longer than any industry standard plating, whether it's zinc-nickel, regardless. Toughshield Plus is a zinc-nickel derivative. It's provided as our standard off-the-shelf protection on all fittings and adapters globally now. So you've been learning that developing an optimal plating system really requires a delicate balance of corrosion resistance, but then also the frictional properties. As Yindong mentioned, zinc-nickel's a little bit, has a different coefficient of friction, different properties. But there's other factors that come into play as well, but we're not going to dig into those deeply today. But there's strength of the plating, adhesion, durability, ductility, to name a few. So this is an illustration here of how Toughshield Plus works. First of all, we're starting with a better foot forward. As you already have heard, zinc-nickel is significantly better than zinc. But Toughshield Plus is actually a proprietary zinc-nickel alloy, as well as processing methodology that we've been working on for years. So the advanced plating structure, as well as application or processing methodologies, is really protected under IP, but in a nutshell, it protects the base metal significantly longer than zinc or commercially available zinc-nickel plating systems. So that's the base layer, protecting that steel substrate. Then what comes next is the passivation layer. It's often called the chromium conversion layer or even chemical conversion layer. Those terms are often used synonymously. It's another thin coating that protects that sacrificial zinc-nickel as well as the substrate. So for years, the industry battled with hexavalent chromium passivation or hexavalent chromium conversion. And about 15 years ago, the end-of-life vehicle directives mandated that we get rid of that in our industry and many industries. So Toughshield Plus continues to be hexavalent chromium free. So just be clear about that. And then something that we're really happy about, the significant advancement here for all threaded fluid power fittings is really the engineered top coat. It provides superior friction and assembly control. It's drop-in compatible, forward and backward compatible with zinc, as well as zinc-nickel. And it allows our customers to maintain consistent assembly methods as well as assembly performance. Again, you heard that. Don't mess with my assembly procedures. But also assembly performance, making sure that it maintains appropriate clamping load. It doesn't back off over a long period of time, etc. So these global plating system, these attributes have been carefully engineered, tested, validated, and across a mass production capability on all of our global steel product lines. So we're very pleased about that. But just how much better is Toughshield Plus? So it's starting off with zinc-nickel, proprietary, but what does that mean to me? Well, you're going to get 3,000 hours of salt spray resistance. So the industry norm is, again, static salt spray testing. SAE requires 144 hours, which is our primary governing body. Typical zinc in the industry is going to be 144 to 500 hours. Typical zinc-nickel is 500, maybe to 1,200 hours, but again, it's highly dependent and a lot of exceptions. And again, tested only to static salt spray testing. Toughshield Plus provides 3,000 hours to salt spray testing. But we're taking that a little bit further, and as you probably gathered through Yindong's discussion regarding cyclical corrosion testing, we're now going to be implementing cyclical corrosion testing and how we qualify our product. We use two fairly demanding cyclical corrosion tests, one being the ISO 16701 cyclical corrosion test, as well as the one that's more common here in North America, which is the SAE J2334. So, and again, the reason why these are becoming more common method of evaluating and qualifying plating systems for corrosion resistance. Some OEMs are already using cyclical corrosion tests, either these or derivatives of these. And again, it doesn't just rely on that static fog. It relies on the alternating cycles of humidity, dry heat, and changes in temperature to provide a bit more realistic approach of what you would see in the industry. So how do these products look in a salt spray performance? So what you see here is a rather large, not large, a modest representation of different products, whether it's a DIN straight fitting, a fitting that has crimp swivel nuts on it, a Boss adjustable elbow that has a backup washer and lock nut on it. These have been tested independently to ASTM B117 or the ISO 9227 equivalent. And so really the takeaway here is that from brand new, clearly up to the 144-hour SAE requirement, no corrosion, no base metal corrosion whatsoever, all the way to triple of the SAE requirement, well past that to 15 and all the way to 3,000 hours, no base metal corrosion. So what you would typically see in a test like this is it would first of all stop at around 1,000 hours, and you would also see a high degree of variation depending on the product. There's going to be products that have no corrosion or little corrosion, white corrosion, red corrosion, and you'll see a lot of corrosion on the products that have heavy metal deformation. But with Toughshield Plus, no base metal corrosion up to 3,000 hours. The only corrosion you will see here is some of that white haze, but again, counterintuitively, that actually is good and helps further protect the product from further corrosion, as Yindong had mentioned. Now, this is a similar sort of grid, but for the cyclical corrosion. We're showing the a 60-day CCT test to the SAEJ 2334 testing. So again, the same takeaway here from 0 all the way to 60 days. That represents one full cycle of this fairly demanding test. Because remember, this test, if you're not familiar with it, includes not only the salt, but it also includes exposure to calcium chloride, as well as some other corrosive agents. So in the cyclical testing protocols. So this truly is a breakthrough and a big difference for the industry. And then finally, Toughshield Plus really delivers significant corrosion protection after a product's been deformed, plated, and then deformed during processing. So that's a significant limitation of any traditional zinc fitting, as well as most zinc-nickel platings. So for components like these, where and our industry relies on these swivel nuts, backup washers, staked products, and even the sharp corners and threads, there's no base metal corrosion even on these compromised components. Compromised meaning deformed after plating, all the way up to 3,000 hours. If you look here at both an SAE test as well as a salt spray test for zinc, you can see that the crimp nuts on these products are already compromised at the bare minimum SAE requirement of 144, and the fittings are fully engulfed in base metal corrosion, basically at 45 days up to 3,000 hours. So this also helps minimize that corrosion migration concept that we just spoke about earlier. So we've made some significant changes in what we're bringing forward as far as our standard plating offering on adapters. But what's not changing is, us and our customers, responsible suppliers and responsible customers collectively want to make sure that there's no adverse effect on the environment. So as you've heard, the industry moved away from cadmium many, many moons ago. But even more recently, in the last 15 years, the end-of-life vehicle directives mandated that we migrate away from hexavalent chromium conversion process as well. So certainly Parker's committed to environmental stewardship. And so while we had to upgrade some wastewater treatment lines as well as the monitoring systems for that, we certainly have no negative adverse effects on the environment. So we're proud to say that Toughshield Plus continues to meet these environmental directives. So I'd like to thank you today for your time. It's our hope that you learned a bit more about corrosion, how it's measured, assessed, as well as tested in the fluid power industry. So, we see corrosion protection as a core competency, and we're very optimistic that Toughshield Plus is going to be a game changer for those customers that rely on us for their fluid conveyance products. I believe we might be moving into the Q&A session. I'll let Bob take care of steering the ship on that.
Thanks, Brian. Thanks, Yindong, for a great presentation. A lot of great information there. And we'll be getting to Q&A here in just a moment. If you still have a question for our presenters, type your question into the Ask a Question box and hit the send button. And also, please take a moment to complete the feedback form that will appear on your screen at the end of our webinar today. A lot of questions from the audience, a lot of different things that we want to try and get covered as we go forward on this. Let's start with, is there such a thing as a special designation for fitting part numbers to receive this Toughshield Plus coating?
Bob, I'll take that one. That seems a bit embarrassed. I may not have covered that. So just to be very clear, the Toughshield Plus is going to be the plating of choice that we'll utilize for all of our hydraulic adapters. So we are not changing our part numbers whatsoever. It is going to be implemented on a running change, however. So after the zinc product is fully consumed and out of our markets and our distributors, as well as our service centers, everything with a normal nomenclature will come through, and it'll be Toughshield Plus. Great question.
Very, very good. And I think you talked about this a great deal, but let's go back onto it because standards are very important to the audience. Have the standard bodies published a cyclical corrosion test?
I would take this one, Bob. Thanks. So I would say yes, as I covered in my presentation, many of those governing bodies, ISO and SE International, they publish several cyclical corrosion test standards, and that's why we choose two of them in our developmental and the qualification process. Even though, I want to make clear, even though SAE International currently do not require cyclical corrosion test in their J514 fluid conductors and connectors standard, but those governing bodies, they publish several of those tests, and they are pretty common in the industry. We select those two for several reasons. One of them is they cover a great deal of geographic areas. The SAE is the most heavily used in North America, and ISO used in other areas. So, yeah, if you are interested, you can look for the specifications for several of those cyclical corrosion tests.
Very good. Another question for the audience. Did you reference that nickel plating affects the threads of the connectors, and could this result in tubing to untorque?
I can actually take this. I use the term drop-in compatible. You know, when the industry upgraded from hexavalent chromium-based zinc plating, was it 15, 6, maybe 20 years ago, to trivalent chromium, the industry actually, fluid connector industry overall, we actually had some embarrassing situations, several manufacturers, where the torques were changed, or the assembly flats or turns had to be changed. So that's some of the feedback that we got, because we talked to a lot of customers before we brought this out, and they said, don't mess with my torques again. So the delicate balance between making sure that it's drop-in compatible, no changes to the assembly torques, no changes to turns, flats, whatever the assembly method might be, because there's a different assembly method for different types of products. Some are torqueable, some are engagement methods, but regardless, the customer base said, don't make any changes to that. And we carefully measured that. That's a big part of the top coat, as well as the testing that was done. So there's a lot of work being done on friction coefficients, as well as measuring retained torque, making sure that the appropriate clamping load or the appropriate applied load is maximized and translated into a torque, or excuse me, a clamping load, so it doesn't back off over time. So I hope that addresses that. There was a tremendous amount of effort undertaking to make sure that it's drop-in compatible.
Yeah, And another question along the same line, somebody asked about the impact of torque values of Toughshield.
I think that was addressed there in my very long response. No impact on torque values.
Very good.
Just want to make it clear,
sure.
It is a Toughshield Plus.
Yeah, absolutely. Here's a very simple question from our audience. Why not just nickel plate?
I will take this one, Bob. So nickel plating is pretty brittle, and it's not sacrificial layer. So it's a barrier layer, but because it's brittle, it's very easy to fracture or crack, and actually render worse performance than zinc-nickel electroplating.
Another question, how does the coating handle wear from tools, and how do the deep gouges affect the overall corrosion rate?
So that's actually a good question. So there's not necessarily a particular industry test for measuring that. Zinc-nickel has a higher degree of toughness in regards to that, but there's not a particular test that we undertook on that. So we say that it's going to be equivalent to our zinc product or better.
Very good. We talked about some of the environmental concerns and some of the ways that the product addresses that. Here's a couple in that area. First, how does Toughshield Plus coating react with agricultural spraying chemicals, and does it provide better protection?
I can actually take that one, Yindong. So yes, actually, we have offered an off-the-shelf or a commercial standard zinc-nickel commercial non-standard zinc-nickel product for quite a few years, and it's really marketed or aimed towards a lot of the agricultural industry, whether it's direct fertilizer contact or whether it's incidental contact. So we're familiar with that, and so certainly we're excited about Toughshield Plus. Ultimately, we'll be obsoleting that product line that we call XTR. And it will hold up better to those agricultural fertilizers. There are no industry standard tests. I'm guessing that question, I can't see the questions now, probably came from someone in the agricultural industry. There are no industry standard tests. So we have some internal tests. They hold up very well, comparable, if not better than our XTR in those tests. But typically we ask the customers to qualify those themselves. We're excited about, quite frankly, reducing some complexity in our product line and offering a better product to all segments.
Very good. And another question along kind of the same line, any input on how this applies to landfills?
So I guess that question can be taken two different ways. So if you're referring to environmental stewardship, as in products that end up in the landfill, certainly Toughshield Plus, as I mentioned in the last slide, meets all of the environmental directives as listed there, the ELV, REACH, ROAS, etc. So we're proud of that, as does our zinc that's in the process of being phased out. If you're referring to, or the question was referring to, equipment that might be used in a landfill for processing that landfill, where there's a lot of nasty stuff going on there, certainly Toughshield Plus will hold up better than zinc. We would say substantially better. But if there's a very particular chemical or catalyst or agent that needs to be tested, we'd encourage a customer to test that on their own. But just off the top of my head, I would say it's going to hold up significantly better on hydraulic equipment that might be used in landfills.
Very good. We got time for a few more questions. What is your baking process for avoiding hydrogen embrittlement concerns?
I will take care of this question, Bob. So let me answer this question twofold. First of all, the Toughshield Plus, as introduced by Brian, is based on zinc-nickel, so it still shares a lot of common similarities with the conventional off-shelf zinc-nickel plating. So for parts that need hydrogen embrittlement relief process, it will still require that. However, for the tube fittings, hydraulic tube fittings and wrappers that we are offering, when I say we, the tube fittings division, that the hardness and mechanical properties of the material we use overall are not as high to hit the threshold where the hydrogen embrittlement relief process or the hydrogen embrittlement concern comes in or the relief requirement kicks in. So for the tube fittings products that with Toughshield Plus plating, actually the hydrogen relief is not, stress relief is not required.
Very good. Let's talk about a couple of other things real quick here. We've talked about its performance, so now we're going to talk about how it looks. There's a question, is there any way to determine by looking at a fitting if it has the old style plating or the new Toughshield Plus?
Oh, I'll take that. Once again, I'm a bit embarrassed I didn't cover some of that. But yes, it does look different. It looks significantly different. So traditionally, our products, as well as most in the industry, have a silver plating on the zinc, silver clear chromate typically, and the color comes out as silver. The Toughshield Plus zinc-nickel is actually gray. So it's a fairly uniform gray product, has fairly uniform look to it regardless of where it's manufactured around the world. So additionally, for those of you that happen to be familiar with our packaging, we also have put some an indicator of that on the packaging as well, on the boxes and bags. There'll be use our logo. So good question.
Very good. Yeah. And can these fittings be painted?
Yeah, let me take you off that. So, yeah, actually both zinc and the zinc-nickel plating, including Toughshield Plus, of course, provide a good paint base. And while during our developmental work, we have not conducted specific paint adhesion tests, several of our OEM customers that they paint after assembly, they continue to do such work without need to modifying their painting procedure.
Very good. And this is a good question, I think, to wrap up our presentation for today. When will the changeover be complete and have some of the fittings already started shipping?
Yes. So as I mentioned, this is Brian. I'll take this one, I guess. The transition should be complete around the end of the calendar year. So, and to answer the question, yes, several of our plating operations globally have already been upgraded to Toughshield Plus. Product is already in our distribution centers. Customers are already seeing it. So yes, it's out. The vast majority of our products, again, being converted on a running change, will be completed or implemented to Toughshield Plus by the end of the calendar year.
Very good. Well, we got a tremendous number of questions today. We weren't able to get to all of them. So for those questions we didn't have time to answer, we'll be getting back to you via email. I want to thank Yindong and Brian for a great amount of information today. And on behalf of Machine Design and Power in Motion, I'd like to thank Parker Hannifin for sponsoring today's event. Of course, thanks to all of you for joining us. Have a great rest of your day and stay safe out there.